See what?
Yeah, what did I see?
Nothing.
Are you tap dancing?
I don't see.
All right,
No,
talk about the distance formula today. Okay? I told one of the classes that over the weekend I'll sit down, I'll kind of scrub through the sections of our textbook, and I'm going to list down, or write down a list of sections in which this thing pops up. Okay? Because I think it's going to be useful for you to see how much we will use this down the road so that you maybe change the way you view it now. Okay? Because some people in the past, it turns out it's not hard, but some people just struggle with it, and they say, well, I'm not going to take the time to mess around with it and learn it to a high degree, and then it hurts them in chapter 3, it hurts them in chapter 4, it hurts them in chapter 5, it hurts them in chapter 6, 7, 8, 9, 10, 11, 12, and 13. Okay? It's in every chapter, guys. So if we don't learn it now, we're not going to have a lot of success later on. Okay? So it's very important that we learn this. And when I say learn this, I don't know, because I don't know if we are going to learn, because we maybe already know it. Okay? You just don't know it maybe in the format that we're going to use. Okay? But there is some nice things about this. You have all the preliminary basic procedures already learned, so that we could just kind of combine them to create this formula. And they're actually pretty easy, okay, individually. When we have the ability to do this, when we have a formula that you guys can go through and see with the algebra that you currently know and understand, see the creation of the formula. We're going to do that. I am not a big fan of saying, here's a formula. This happened to you last year, and it's no fault to the algebra teacher, because you don't know enough algebra to do this yet, to know where this formula came from. Don't write this down. But you had that formula last year, right? You do not have enough algebra skills at the moment to understand why that formula works. Okay? Because you have enough algebra skills to use it, and you need to use it at the stage of Algebra 1, but you don't have the skills yet to understand why it works. Okay? When we, and that happens a lot in math, guys, when you have the ability, you have the algebra skills to use a formula, but maybe don't understand really the place and where that formula comes from. It happens all the time in algebra. It might not be 2 years, 3 years from now that you can talk about where that comes from. Okay? But when you do, it'll make that thing a whole lot simpler and easier to use. Today, the formula we use that I'm going to give you, we have the ability, we have all the preliminary information to piece together and come up with what we call the derivation of the distance formula, the creation of the distance formula. It's all math that you guys are aware of. Does that make sense? The math to do the quadratic formula there, you need to be able to complete the square. You guys ever heard that phrase before? Did you complete the square last year at all? Okay, you did a little. Okay, so you completed the square, but there's a lot of analytical algebra that has to be done with that. We basically take a lot of numbers out and replace with a bunch of variables. And your skill level might not be at the level needed to really be proficient at that. Okay? But with what we do today, you should have the skills to do this. Okay? So this is kind of an investigative approach to a formula. I think by doing this, you're going to remember this formula a little bit better. You're going to be able to use it a little bit better and understand where it came from. Answer questions about it on the end of course exam. Okay? If I just give you a formula and I tell you to memorize it, you're going to lose that in 2 weeks. It's not going to be with you very much or very well. You're going to lose it in 3 weeks, 4 weeks. You're not going to be able to retain it. 4 weeks from now, I take a test, and one of these questions pops up, and you have to use the distance formula. And if you I told you to memorize it today, you're probably not going to be successful in that question. But if you build relationships and you understand where it comes from, why it looks the way it does, if you do ever forget it, you can go back through this process or try to deal with these relationships to generate it again. But you develop a much better understanding of it. Okay? You can use it better, you can recall it. You guys have all crammed for tests before, right? Okay? And whether that worked or not for you on the test, let's say it worked for you. If I ask you a question about that information 2 days later or 3 days later, are you going to be able to answer that very well? No. Okay? It's because you try to memorize things. Okay? That's what cramming is, right? Memorization will fail you in the long run. Okay? That long run might be 2 days, 3 days, it might be a month, it might be a year. But eventually it fades from you. Okay? If you can develop relationships and connections, it's going to stick with you a lot longer. Okay? So that's what I try to focus on in mathematics. Not memorizing steps and procedures and that kind of stuff, but just understand how everything works together. All right? So I want to just ask you a few questions real quick. I give you that segment right there. Okay? Horizontal, right? What's the length of it? 4. Right? Pretty easy, correct? Who counted to find 4? Okay? Let's try not to count. Okay? That's nothing wrong with that, but if I start moving my points around, now if I count, that's going to be a little bit harder, isn't it? Because of those coordinates where they're located. Okay? What's the better way of finding the distance? Subtract the what in this case?
The x's.
Subtract the x's. Okay? If I want to find the length of a horizontal segment, all I have to do is subtract the x coordinates, right? Is that right with everybody? Okay? Traditionally, yeah, counting is okay. Okay, if I'm stuck at integer values, counting is absolutely correct. I would caution you against that for the reason of when it turns into messier coordinates. But even in this situation, let's say that I want to look at those y values. If I count there, look at my grid. If I count my grid, it's three grid lines, right? But what does it actually turn into? A distance of 6, right? So the way that we kind of scale our graph might be troublesome sometimes in regards to counting. Okay? Counting is not the best approach. Okay? If I start giving you fractions up there, start giving you maybe variable values, okay, arbitrary values, counting is going to either cause you really big problems or run you into a roadblock. Okay? But you guys know that's 6, right? You take the 8 minus the 2. All right? So those are distances. That's how we find distance in a vertical fashion, in a horizontal fashion, right? Okay? All right, let me ask you this question. Anybody know how to find that distance? Okay, well that'll give me, that might be something that we can deal with. He said rise over run. Okay, rise over run refers to the what of that line? The slope, okay? Now the slope is tied to distance, or distance is tied to slope. But can I simply, like with the horizontal lines and the vertical lines, can we just simply subtract the x's and get an answer? Or subtract the y's and get an answer? Can't do that, can I? Okay? Because there's a horizontal component and there's a vertical component to that. So I can't just use just the x's or just the y's.
Would you use the Pythagorean theorem?
Okay, so what's going to happen here, guys, is that no matter where I draw that segment, no matter where that segment is created, is it the hypotenuse of a right triangle? Okay? And I'm going to start readjusting it, and you tell me if it is ever not the hypotenuse of a right triangle. You can start trying to convince yourself that that's always going to be the case, right? The only time that's not the hypotenuse is when it's vertical, which if it was vertical and I wanted to find that distance, we already have a tool to do that, right? Subtract the y. Or if it's horizontal and I want to find that distance, don't I just subtract the x's? Okay? But every other time, like Kinnison told us, we're going to use the Pythagorean theorem. Okay, so let me go back far enough here. That should be good. All right. So we want to use the Pythagorean theorem. Does anybody remember what the actual formula of the Pythagorean theorem is? A squared plus B squared equals C squared. Okay? Where A and B are legs of your right triangle, right? Okay? So I'm going to plug in, let's put A here and B there. And there could be flip-flop, it doesn't matter which one is which. But C we usually let be our hypotenuse, right? Okay? I'm going to write it maybe a little bit differently than what you stated. I'm going to write it as C squared is equal to A squared plus B squared. Doesn't really say any, I just used a symmetric property equality, flipped it around, right? There's going to be a couple different reasons throughout the year why I think it's important to look at the hypotenuse first, and then the sum of the other two sides second. Okay? But that's the Pythagorean theorem. That's something you guys have used before. And you start plugging things in, you plug your A in, you plug your B in, or you plug in the two parts that you know. And sometimes you know this, the C and the A, you try to find B, or vice versa. You plug things in that you know, and at the end, if I know A and B, and at the end, I would then add them together. I would take the power of 2, and then I would square root everything, right? Because we're trying to find C to the first power, correct? So I'm gonna actually do that first. We can take the square root here first, and square root there first, and get C, which is representing the hypotenuse, as the root of A squared plus B squared. Okay? I want to show you a little demonstration as we walk through some of the algebra throughout here. I want to kind of go to the side and talk about why is this true. A lot of people make the argument that they want to take, when I take the square root and I get C is equal to this, they then want to do this. Anybody want to do that? Because there's powers of 2 with the A and the B and the square root. We know powers of 2 and square roots are inverses, right? So they should cancel each other out, right? So everybody wants to do, or not everybody, but a good majority of people want to do this throughout the year at some point. My question is that possible? Can we do that? And whether you know the specific algebra, the kind of the, you're going to hear me call it the analytical algebra, that I can actually go through the algebraic proof and say that no, this doesn't work. You could do something. You could try something here to see if you can convince yourself that it doesn't work.
So if you're saying that, then you're saying A plus B equals C. So if I took B was 7 and A was 4, then C would have to be 11.
Okay, so you're saying let's choose just arbitrary values for A and B and see if plugged in here, they give me the same thing plugged in here, right? Okay. Now you said 7 and 4. I'm going to use a little bit more convenient values, I think, for just this demonstration. Let's say that A, so let's just say that that horizontal distance ended up being 6. Let's say the vertical distance, for some reason, whatever the coordinates were, ended up being 8, right? If I start plugging that in here, okay, so it's saying A is 6. So 6 squared would give you what? 36. B squared would give you 64. That adds together to give you 100. What's the square root of 100? 10. Okay? So this right here gave me 10. C to be 10. If I come over here, what's A plus B going to give me? 14, right? 8 plus 6 is 14. Is 10 equal to 14? No. So that's an example. That's what we call a counterexample to this. Okay? This shows, that counterexample shows that this is false. That is not true. Okay? So we can't do that algebra. We can't just let those powers of 2's and that square root cancel out in this situation. Okay? Ultimately, if it's a sum or a difference underneath the roots, then they can't cancel. If it was all product, if it was A squared times B squared, you can rewrite it as AB. Okay? But if it's multiplication, if it's addition or subtraction, you can't cancel those things out. Down the road, maybe later on, we have a little bit more time, we'll talk about some of the laws of exponents that are kind of at play there that guarantee that we can't cancel out that way. Is that okay with everyone? Okay. But that's the Pythagorean theorem. In 7th grade, 8th grade, 9th grade, when you guys saw the Pythagorean theorem before, it was probably, like I said, presented this way. Okay? When you start getting into higher level math courses, the Pythagorean theorem is always kind of published this way. Okay? Because ultimately the purpose of it is to find a linear distance, okay, to the first power. So, what we would have done in this example down here to find this distance, now that we know what A is, because you told me A was 5 minus 1, right? Which is 4. So you plug 4 in here. You told me this distance here of B, I think that's a 7 up there. You take B is equal to 7 minus 2, right? Maybe if I get rid of my axes, it might be a little easier to see. 7 minus 2 gives you then 5. And you put 5 in here, and you square that, right? So what's 4 squared? 16. What's 5 squared? 25. 16 plus 25 is 41. Okay. We'll talk about simplifying radicals here eventually. But 41 is prime, so it doesn't simplify. That's the distance there from A to B. Okay. We'll come back and do some examples, use GeoGebra to validate that. But that's how we do it. Okay. Now, a lot of times, the way that we were able to develop that was through the use of that picture, right? Had to have the picture, had to have that right triangle, had to go through and locate, A and B's coordinates, because this is what you're going to probably be provided with in regards to the problem, okay? If I wanted to use this route, I had to take time and come up with what that third point is. And that might be sometimes hard to do, okay? Or T is for some people to recognize. So what we do is we come up with a formula that's going to make it a little bit better. It's just should be okay. Low battery. That's all right. Thank you. So what we need to do here, guys, is come up with a way that gets us a formula that we don't have to draw the picture, and that just by plugging things and plugging values in for our A and B points, we get our distance. Okay? So this is how we go about doing this. We take and relabel those points as x1, y1, and x2, y2. Remember doing that last year? You dealt with x1, y1, x2, y2. What aspect of Algebra 1 did you do that stuff with? Rise over run. You did it with slope, right? Okay. If you remember slope as rise over run, this is going to be a very easy process for you because it's really the same thing. Okay. This point here has to change. To see this formula that we come up with, we have to know what C's coordinates are as arbitrary values. So x1, y1, those are just any random values they want to be, right? x2, y2 are any random values that they want to be. Okay? So C, we want that to be arbitrary values as well, variable values. Okay? So somebody earlier today said, well, let it be x3, y3. That's okay, but it brings in more variables, which is kind of a problem. Okay? We want a formula that only incorporates the ordered pairs that the problem provides us with. Those are the ordered pairs that the problem is going to provide us with. We don't want x3, y3 because we would then have to find what that ordered pair is based off the ones they give us. So we don't want that. But if I look at that point C, do you know, based off of x1, y1, and x2, y2, do you know what point C's x value could be relabeled as? And let me ask you this. Are there any points on that blue line that have an x value that is different than any other point on that blue line? So I should be able to take any point on that blue line. And I should automatically know what its x value is. I don't know necessarily what its y value is, but I should know automatically what its x value is based off of knowing one of the coordinates of a point that's on there, right?
Since C's x is 1, they're all in the same x line, so
Okay, so you're saying every, because if I look at this point here, because it's 1, then every point on here is going to be 1, right? But I want to go the reverse way because I want to get this changed to a variable. If that's x sub 1, isn't every other point on here called x sub 1? Does that make sense to everybody? Okay? So I'm trying to get rid of the 1 and the 2 and trying to rewrite them as arbitrary value. Okay? So I can call that x value x sub 1. Okay? Every point on that blue line is going to have the same x value. Every point on the red line is going to have what y value?
X, Y2.
It's going to have the y value of y2. Okay? So I'm going to change that. Go caption. Okay? So what that means to us, guys, and even if let's do this. Maybe you can visualize it because I know some of you might be thinking, what is he talking about? Let's do this. Now I've brought back the actual values that are being hidden behind those x1, x2s, y1s, y2s, that kind of stuff, right? Do we see here, x1, y1 is 1, 7, x2, y2 is 5, 2. Do you see at this point right here, its x value is the x value that came from here, right? It's the same 1, right? Is that y value the same y value that came from over here? If I started moving, I won't do this because, I can't. If I started moving this point and that point, this one here will always have that point's x value, and it'll always have that point's y value. Okay? So, leaving it though as variables, x1, y1, x2, y2, allows us to create a formula that will work regardless of where these points go. Okay? Alright, so I want to do this. There we go. Do you remember when this was like maybe 10 as an x value and this was 2 as an x value? You did what with those to give me that distance? Subtracted them, okay? So in this situation, if it was 5 and 1, you gave me 4, right? Okay? But if I don't know what they are, I should still be able to do their subtraction that way, right? Does that make sense to everybody? Okay? Now, it's a distance, right? So it didn't really matter. I could have done this. Could I go 1 minus 5? You got negative 4. But then I would have had to take the absolute value. Good, okay? So instead of writing x2 minus x1 that way, let's write it this way. Okay? And now we have a generic way, a formula essentially, to find the horizontal distance of any horizontal line, right? Okay, we've done that. We said that back in like section 1.2 or 1.3. Okay? And when I want to find the length on a number line, I simply take the 2 coordinates and I subtract them, and then I take the absolute value. Okay? Now, let's talk about doing this for these points on this vertical one. I take 7 minus 2, right? 7 minus 2 gave me 5. Okay? Or I go 2 minus 7 and give my 5 that way. Okay? But take the absolute value, correct? So in this one, you're going to take your y values. And you're going to subtract those. Take the absolute value. Is this okay so far? Okay. Now, remember, the idea or the concept that is tying all this stuff together is that A squared plus B squared should equal C squared, right? But now, I've got a different way of writing A and B. A was the length of this leg, right? Well, now we've got the way of writing it that way. B was the length of that blue leg, and we have the ability to rewrite it that way now. Okay, so I'm going to come over here to our formula that we said was C was equal to A squared plus B squared, right? But now we know A is going to be x2 minus x1, and then we'll square that. Is that okay with everybody? The B becomes what we've got here in the absolute value bars. So plus y2 minus y1, and then we'll square that. Good so far? That's just substituting, right? Okay. Now, here's the thing. Our formula does not know what I let x1 and y1 and x2 and y2 be. So these two things could be flip-flopped. It could be x1 minus x2. It could be y1 minus y2. Okay. That order really doesn't matter because of the fact that we're taking the absolute value, right? So 2 minus 3 is negative 1. 3 minus 2 is 1. Take absolute value of both those, I still get 1, right? So order of subtraction doesn't matter if you take the absolute value.
Why do we square them if we're going to square them?
Because it was this idea here, okay? Because we're going to add them, we're going to square them, then add them together, and then take the square root, so that those things can't disappear. Okay, so here, before we go to the next, a lot of times your textbook or any publication that you see with this next step just kind of writes it out but never explains where things kind of disappeared. Okay, so I want you guys to kind of help me here. What does the absolute value operation, okay, do to any value? Makes it positive. That's the only thing it does, right? Absolute value has one task, makes the value positive. Okay? Makes the value positive. What does the power of 2 do to something?
Multiplies that number by itself.
Okay, so let's write this. So power of 2, or sometimes we call it squaring, right? Okay. You said it multiplies a number by itself. Absolutely right. And that's going to make that number, so say that number is 2. Multiply it by itself, it goes to...
Its own absolute value. It multiplies it by its absolute value.
Not necessarily. I mean, maybe you could think about it that way, kind of. I don't know if that's a real safe way of thinking about it. But what do I get if I take 2 squared? I get 4, right? It took 2 and made it...
Bigger.
Yeah, it made it bigger, right? Okay. Now, it doesn't always make things when I square, so it doesn't always make something bigger. If I start with a half and I square that, what do I get? 1/4. So it made it smaller, right? Okay. But it changes the value, right? It changes the value, changes the size, correct? So let's talk about the things that squaring does. It changes the value or changes the size of a number. Okay. But what else does it do? It guarantees the number that I get. It guarantees my product to be what kind of number? Guarantees to be positive. So there's 2 things here it does. Okay? So this is the absolute value, and this is the power of 2. And now the reason I want to talk about this is because that's what's happening to my x2 minus my x1. It's being applied with the absolute value first, and then we're squaring that. Well, doesn't this squaring take care of this absolute value? So does that prove to you or show to you that that absolute value there is kind of redundant or unnecessary? Does that make sense? Because it's an operation that's being done twice. I make it positive the absolute value, but this is also going to make it positive. Okay. So what happens a lot of times, guys, is textbooks will do this. They'll write, it's terrible. They will go from that step straight to that step and not explain where the absolute value bars went. They just say you can get rid of them. Okay? Well, we can get rid of them or delete them out because the purpose of them is already being done by the power of 2. Okay? So we don't necessarily need them. Does that make sense? But I can't get rid of the power of 2 and keep the absolute values, right? Because the power of 2 is doing something extra that the absolute value bars do not do. It's making that value change, right? Okay? So you can't just choose which one you want. You got to choose the one that is getting taken care of by the other operation. Okay? So that's kind of the math that's, people think math is just doing calculations, right? I think that is more, understanding that is more math than any calculation that we're going to do. Okay? If we can understand the fact that how the absolute value and the power of 2 kind of work together in this situation. Okay? Now, another thing that I think is important. Because we're squaring, I might get like -2 here. Or I might get +2. Does it matter? Because when I square it, what do they both give me? They give me +4, right? So when I go x2 minus x1, because I'm going to square it, it doesn't matter if I would have gone x1 minus x2. Okay, so if I have like two x values that are 10 and 4, if I subtract them 10 minus 4, I get 6. Square that, get 36. If I go 4 minus 10, reverse the order, I get -6, but what's -6 squared? Still 36, right? Okay? So traditionally, normally, all by itself, subtraction, you cannot change the order, right? You guys remember what that property is called? When you cannot change the order, or that you can change the order? Okay, the commutative, okay? So subtraction is not commutative, okay? But when I square that subtraction, it doesn't really matter the order, okay? Now, my other question is, does it matter the order of this and that? Can my y's be here? Can my x's be over here? Yeah, because addition is commutative, right? So this might end up being like 16, this might end up being 30. Well, 16 plus 30 is 46, but what if they flip-flop? Is 30 plus 16 still 46? Yeah. So the reason I talk about that is because there's a lot of different variations of this formula that you might see. You might see the y's come first, okay? You might see the x's come first, like we do up there. You might see it x1 minus x2, and y1 minus y2. Does that make sense? There might be 4 or 5 different versions of that formula that you see, but understand that we treat them all the same way because of those operations, okay, in regards to their commutativity and the power of 2 there. So, a lot of times we don't call this C though. When we talk about the distance formula, we call it D for distance, okay? And that then allows me, guys, not to have the picture, okay? I don't have to draw a picture. I don't have to find that third point, C. You notice up there, there is no, that's a formula that does not incorporate x3 and y3, right? Okay? So that's a nice thing here, okay? So this point here doesn't incorporate any of that. But what did this come from? It just came from this, didn't it? What was this? Pythagorean theorem, right? So when you guys see that formula, and they ask you questions about it, okay, and maybe they ask you, where does it come from? How did you come up with it? Or something like that. It's just the Pythagorean theorem. Or they say, what is the distance formula? It's analogous, or it's the same thing as the Pythagorean theorem. All right? Is that cool? So that's the creation or the derivation of it. Now let's use it. Okay, let's do an example. Let's go back to showing the values of these. I don't need. So this is kind of what's going to happen initially, guys, is that they're going to give you either a picture graphically where they say here is point A at 1,7, here's point B at 5,2. Find the distance between them. They might write out in words, okay, no picture at all, and inside those words they give you 2 points, 2 word pairs, and ask you to come up with their values, okay. Something that I didn't mention, but you guys were kind of hinting at it before we get into this example. Somebody talked about slope earlier, right? When you do rise, isn't that your y2 minus your y1? Think about your slope formula. Slope formula was y2 minus y1, right? Over x2 minus x1. Once you do your slope, you have the components to do distance. Does that make sense? Now, in slope, you're dividing those components, right? In distance, we're going to square them individually and then add them together, and then take the square root of that sum. But you got the individual pieces. Okay, you've got your rise and run. So some of you might be, if you're scared of this formula or it's bothering you, maybe you can rewrite it this way. Distance is equal to run squared plus rise squared. Would that be fair to say? Okay. You've got options. with writing that formula. Now, it'll never be presented to you in any textbook that way, or any, standardized test formula sheet that way. It'll be what I've got up there in white. But that's an option, okay? When you guys take the standardized test this year, in the past, the end of course exam has had maybe 4 or 5 questions that deal with the distance formula on it, okay? And different aspects of geometry, different areas of geometry. I don't think they give you that formula, okay? In my course, in most of my tests, I don't give you formulas because you will get a formula sheet on the end of course exam, but it's just a handful of formulas that are common. Will I use all those? Probably not. Will I use some of them? Maybe. Will I use some formulas that are not on that sheet? Absolutely. Okay? So my thought is if I never give you a formula, make you learn them all, then we get to the end of course exam, when they give you some that you need, awesome, it's a great day. Okay? It's bonus for me. Okay? So keep that in mind. This formula I'm not going to give you on a test or a quiz. You're going to have to know it. Okay? That's kind of all year long. All right, so let's do the exam. Let's do the problem. Hopefully you see that once you have the formula written down in front of you, it's pretty straightforward. Plug my x2 in. What's my x2? You guys understand this notation when I go x2, y2 is equal to this, so the x2 respectively is 5. What's x1? 1. Okay, what's y2? 2. Y1? 7. Okay. Don't grab your calculators. We shouldn't be able to use our calculators. You don't need to. What's 5 minus? Order of operations says do these subtractions first. 5 minus 1? 4. I'll have that squared in a moment. Plus then 2 minus 7? Negative 5. Okay? And I'm going to do that. I'm not going to, when I get a negative result and there's still an operation to be done to that negative, like a power here of 2, I'm going to put it in parentheses. And I'll show you in a moment why I think that's important for us to do, especially if we are a person that uses our calculator. What is 4 squared? 16. What's negative 5 squared? 25. 16 plus 25? 41. Okay, that's kind of disconcerting. So 41, okay, 41. Now 41 is a prime number, so this thing does not simplify. Okay, we'll leave it as 41. Radical 41. Your Math Excel sometimes will ask you to leave it as radical 41. Sometimes they'll say, okay, you can take the calculator and see what that decimal approximation is. We'll talk about that here in a moment. The reason I think it's important for us to not grab our calculator is to understand what is actually going on here. Okay, I use the analogy to last class. I said if you've all met somebody that's like sprained their knee or messed up an ankle or something like that, the trainer gives them 1 crutch, right? Okay. If they give me 2 crutches, I'm probably pretty good at using those right off the bat without any explanation of what to do, right? Okay. But if they give me 1 crutch and my right leg is bummed and they give me 1 crutch, it's probably a good idea for the trainer to tell me what arm to put that crutch under and what arm or what leg to use with that crutch. Does that make sense? If I don't, I'm probably going to damage my leg even more. If I put it under my right leg's hurt, put it under my right arm, and then lift my left leg. That's going to be kind of silly, right? So I'm going to damage my leg even more. So that's my thought with my calculator, okay? If I don't know how to use my crutch, I'm going to damage my body, right? If I don't know how to use my calculator, which is essentially my mathematical crutch, if I don't know how to use it, I don't know what it's doing for me, I'm probably going to damage my mathematics skills, okay? What I mean by that, you guys have all seen this. You do this in Mrs. Cole's class last year, okay? I know because I had her too. Okay, so you get your calculator out. First day you start talking about exponents, you do something like this. You say, I want to take -3 and multiply it by itself. Well, we know that's squaring, right? And you get -9. But based off our logic, -3 times -3 should give me what? +9. My calculator messed up, right? No, I don't understand how my calculator works. That's why it's wrong. Okay? The calculator is viewing it this way. The calculator is viewing -3 as -1 times 3. Does that make sense? And then the power of 2 is there. And our laws of exponents say the power of 2 is applied to the object that's directly behind. What's it directly behind right now? just the 3. So it squares that, because that's what order of operations tells us to do. PEMDAS tells us to square that first, right? Gets me 9. And then it multiplies the 9 by -1. That's where I get that -9, right? So what do I have to do? I have to tell the calculator, square that -1 as well. Okay, so we do it this way. -3 squared. And now that's essentially telling your calculator, take -1 times 3 in parentheses and multiply that by itself. So if I do that, does that give me my 9? And that's what we think we should get, right? And we're telling our calculator basically, this is the way it's thinking about it, to do that. Square the -1. What's -1 squared? 1, right? Square the 3. What's 3 squared? 9. What's 1 times 9? My 9, right? Why do we talk about that? Because somebody inevitably will want to take this down here, which we know to be radical 41. Let me see what radical 41 is. A little bit bigger than 6. Okay, 6.4. And they want to do this at this step right here. They want to take square root. And they're going to go 4 squared. Perfectly fine so far. And then they want to go plus, and they go -5 squared.
Teachers and students, pardon the interruption for one more afternoon announcement here. Just a reminder that beginning this weekend, all right, the asphalt project will be taking place here on campus, particularly pertaining to Monday, the south lot, again, by the trophy case entrance and softball, baseball field, that lot all the way back to the baseball diamond. Excuse me, will be paved and being worked on. Students are going to have to park out in the band parking lot and near the baseball field. Excuse me, on Monday. Students can use door 5 to enter the building on that day as well. Sorry, guys. Just a reminder, too, that for the drivers after school and those being picked up, you guys will not be able to get off campus until the bus leaves, which will be approximately 3:25 each day. Again, if you drive or have parent pickup, you will not be able to get back off campus until the buses leave at 3:25. Hope everybody has a great weekend, and good luck tonight, football team. Thank you.
All right, so on this situation, when I type it in, guys, it gives me an error that says non-real answer, okay? That would maybe be insight that I've done things incorrectly by the way I typed it in, but that won't always happen, okay? That only happens because there's a negative underneath the radical when I'm done here, okay? If I were, let's say if this number here was like a 3 instead, a -3, okay? So if that was a -3 square, it should give me radical 25, which would be 5, right? Does that make sense? If I type it in this way, where that's a 3, see if it gives me radical 25. It doesn't, okay? But if I don't know that my calculator is doing that -3 and squaring the 3 only and keeping the negative, I'm going to take that answer for what it's worth. I'm going to say that's the right answer. But I type it in, it's wrong, right? Does that make sense to everyone?
Yes.
Okay? So we have to understand what our calculator is going to do if we're going to use it. If we're not going to do that, guys, my suggestion, don't use your calculator. Okay? You know what? My philosophy is, you know, if you're on a way, I talk to, you know, previous football players and stuff like that. They'd always ask me, can I take a supplement or something like that? Well, if you don't know what that's going to do to your body, don't take it. There's not enough research to say this is what it does to your body, don't take it. So if I don't know what my calculator is doing for me, don't use it, right? Okay? So think those things through before you start grabbing your calculator and trying to do all that work with it. In your homework tonight, there will be times, we didn't get to an example, but there will be times where they ask you to simplify radical. So take like radical 45 and rewrite it as 3 radical 5. Okay? It's a Algebra 1 prerequisite. You guys did it last year. But again, I understand you might be a little bit behind with some of that stuff. So if you go down to this box down here on the website, go to see where it says radicals, click on that. There's going to be some applets I created here to get practice at simplifying radicals. Okay? But if you don't know how to simplify radicals, I think there's like 5 videos here in this column. They'll walk you through the prime factorization process of simplifying radicals, okay? If I have 108, right, the radical 108, we don't want to type that in as like 10 point whatever it is, 10.2, 10.3. We want to simplify that down to something else, okay?
Was that you before you had the beer?
No, that is not me. All right, so 1.7 is online. You should be able to access that, address it. Like I said, there's a couple, and then if you guys simplify the radicals, the rest of them, say grab your calculator and round to like the nearest hundredths or thousandths place or something like that. Okay. Have a great weekend.
So go close and